So, we were discussing stop flow, right. So, this is what we looked at last class. It is a part of a rapid mixing technique. So, this is what the stop flow is all about. You have two syringes, one with protein and high concentration denaturing, and the other one is buffer, and there is a third syringe which is known as a stop syringe, which stops the flow. So, after the flow is stopped, you can see this is your observation cell, right. This is the observation cell, and you can see what happens is this is where you make all your measurements or your data collection. So, what happens is whether you have whatever technique you are using, say in this case we are using a fluorometer, then what would happen is the excitation light of the fluorometer, that is of the lamp, would come like this, and then you collect fluorescence at right angles, but essentially that is your observation cell. So, you have stopped the flow and then you are watching the protein to fold back to its native state at whatever final denaturing concentration you have. Okay. So, just hold on with the technique, I will come to the technique later. Technique means the spectroscopic tool, which is fluorescence, but just focus on the technique right now as such, right, the stop flow. Okay. So, essentially you stop the flow and then you are watching the protein to fold. So, again to put things very simply, what you are doing is once the mixing is complete, right, you have completed the mixing, then the stop flow syringe gives a stop signal. The protein has already seen the low concentration of denaturing, right, because you have mixed it, but the protein cannot respond just like that. It takes time to come back to its native state or whatever state under these refolding conditions. So, that is the time you are monitoring. Okay. Now, one thing which an error I made last class was, I will tell you what I was what I am referring to right now. Okay. So, but before going there, this is a change you are looking at. So, in this case you are looking at a change in fluorescence. So, the native or the folded is typically an emission spectrum of tryptophan. If the tryptophan fluorescence would decrease, in this case you can see when you go from the folded state to the unfolded state, the fluorescence is decreasing. So, if you are doing a refolding, that means you are going from unfolded to folded, what would happen to the tryptophan signal? It would increase. So, you would see an increase in the tryptophan signal, right. So, on the contrary, I was taking a case which was cytochrome C, and where I said just the reverse happens, because in this case the tryptophan, there is only one tryptophan, which is tryp 59, okay, at the 59th position. In the native state, tryp and heme are very close to each other. Tryp transfers almost all of its energy to the heme. So, this folded state has the lowest intensity for tryp and the unfolded state has the highest. Okay. So, then this is how it looks. So, this was about cytochrome C. Let us look at the spectrum. So, this is how it looks. If you go from the unfolded to the folded, what will happen is your tryp intensity would decrease, and that is what you are going to monitor as a function of time, and this what you are looking at is a change in fluorescence, right. So, then at the very end of the class, what we are looking at is something known as a burst phase, and now what did we say burst phase was corresponding to? It was corresponding to some time known as a dead time. So, this is the error, this is where I made the error. So, when I wrote the expression or definition for dead time, what I said was it is a time lag between when you complete mixing. Actually, that is not true. What I meant was it is a time lag between the time point you start mixing, that means initiate mixing, not complete mixing. So, change complete to initiate. The time lag between you start initiation of mixing, there is a first time you start them mixing them, and the first time you collect your data point. So, the first time you start mixing the solutions and your first data point, this is the time lag between which you do not have any information about the system, because you are not being able to collect any data, right. So, that is your lag time and that is your dead time, because that is dead for you, you cannot see anything or you cannot see anything with regards to the system, right. So, any conformational change that happens during that phase is referred to as a burst phase, because it happens in bursts, because it happens so quick for your instrument that you cannot catch it, that is why it is called a burst phase, right. Okay. And then what we also said was, so this typical trace you are looking at, this trace what you are looking at is the final concentration is 0.7 molar denaturant, say guanine hydrochloride, right. Where they started from was a concentration of 4.5 molar guanine hydrochloride. Okay. So, initially the protein was taken in 4.5 molar guanine hydrochloride, and then you mix buffer into it rapidly by the stop flow technique, such that the final concentration is 0.7 molar of guanine hydrochloride, clear, and that is what you are looking at, that is the kinetics you are looking at. So, the protein would stop at this signal S infinity, and what does this signal at infinity mean? It means that this is the equilibrium signal of the protein at 0.7 molar guanyl hydrochloride. That means the final denaturing concentration. Clear? So, this is the final signal you have, right. Okay. So, this was at S infinity. So, there is another thing called S 0. So, if S infinity has T infinity, then S 0 is your T 0. So, T 0 means the time 0. Now, this time 0 is not with respect to your initiation, this time 0 is with respect to your first data point you are collecting. Please keep that in mind. With respect to the system, the time 0 has already started a long time back. You have not been able to look at it because that was in your dead time. So, time 0 is always with respect to your instrument. That means how fast or what is the first point you can capture, that is your time 0 essentially. 0 time and then your time evolves. Okay? That is what the 0 time is. Okay. So, then we were discussing one question. The question was, what is the significance of this S u predicted? That means signal, u means unfolded state and predicted means what do you predict? Where do you predict it from? And this is where we were talking about equilibrium transitions. Okay. What did we mean by that? So, let us so what you can see out here is written for the same graph. The conformational events occurring within the dead time referred to as a burst phase, and here the final denaturing, which is guanyl hydrochloride concentration, is 0.7 molar. So, well, I mean, before going further, let me tell you what you do is you look at all these points. You see, look at all these points, these circles are your data points. Okay. These circles are the points you collect with the help of your instrument. These are your points at different time intervals, right, or different times. These are your kinetic data points. Now, obviously, once you get a kinetic data point, what would you do? You would try to fit it to a model. Now, this is an exponential model you fit it to, assuming that it is kind of a two state process, right, though it is not. You are looking at activation barriers, exponentiality comes from that, but what you fit it to is this. Say this is your S, that is a signal t, if this is your S, that is signal t as a function of time, and this is what you fit it to. You fit it to a summation of a I e to the power minus k I times t plus S infinity. Okay. So, what do we mean by this? So, S as a function of time, you can realize it is your signal as a function of time, right, fluorescence signal. Then what is S infinity? S infinity means everything is done, this is the final state you have, equilibrium. Okay. That means your signal at infinite time, but look at this one, a e to the power minus k t. What does it mean? I is, so what you can realize is it is an exponential fit, right, because e to the minus k t. So, what does I mean? I means that you might be having more than one exponent coming in. So, you might be having say I is equal to 1, 2, 3 depending upon how many exponentials you need to fit it. So, it can be mono exponential. If it is mono exponential, then I would be equal to 1. If it is a bi exponential, then I would be equal to 2. If it is a triple exponential, I would be equal to 3 and so on. So, then if I refers to that exponential time constant tau or k, in this case k, the rate constant, what does A refer to? A refers to the amplitude. That means in the total signal, say if you have, say in the total signal you have just one component. What is the amplitude? It is no big deal, the amplitude is 1 because you just have one component. Now, suppose you have two components, I is equal to 1 and I is equal to 2. It might be that both the components contribute 50%, that means equally to that decay. So, in that case A1 and A2 would both be equal to 0.5. It might be that one contributes 20%, the other one contributes 80%. So, in that case for the 20% A1 say would be 0.2, for the other one it would be 0.8 and so on. So, this is what amplitude means, that means it is the contribution of that respective k I component to the exponential decay. Is it clear? Right. So, this is how you get your kinetic information, that means the kinetic parameters, in this case either the rate constant k I or the inverse of that, which is the time. That is what you get from here. Okay. And that is what you finally use. Remember, where do you use it? You use it and with the help of something else you construct your chevron plot, that is how you do it, but this is how you get your k from here. Okay. Now, This is what I meant by SU predicted. So, look at this. This is not a time curve. What you are doing is you are doing a chemical denaturation of the same protein, right. You are going from the folded state, which is at the left. You can see this is your folded, right. This is the folded state because you have low denaturant, and this is your unfolded state, right. It is written folded, obviously it is written on the top. This is unfolded state. Now, see how it matches. This is the fluorescence. In the folded state, the fluorescence is really low, is not it? So, that is why it has the value is low. It is also S infinity. Why is it S infinity? Because whatever you are doing it at equilibrium, and this S infinity is the same S infinity you are getting in your kinetic trace. Do you realize that? Think of this. Say, what was the final denaturing concentration in the previous case? It was 0.7 molar. Okay. So, say this is 1, this is 0.5. Say this can correspond to 0.7, right. So, what S infinity means is whatever equilibrium value you have at this point, that means for 0.7 molar guanine hydrochloride, whatever equilibrium value you have from your thermal denaturation of fluorescence should match with the one you get from your kinetic trace, because you are finally talking about equilibrium time. S infinity is essential equilibrium. One point obviously I can realize that you will not be able to kind of make out is how to match these two things. Their units might be different, here units might be different. So, generally then what people do is they plot ratios, okay, so that whatever you do, the final thing comes out to be independent of whatever you started with, right. They plot a ratio of signals, but anyway guys, do not worry about that. So, this is how it is done. This is how you match it between the equilibrium value and the kinetic equilibrium S infinity. Okay. So, just before leaving this slide, you look at SU predicted. Now, this is important. You look at this dotted line. Can you tell me what is this dotted line referring to? First of all, where is this dotted line coming from? It is coming from the unfolded state. If you recall, when we were actually going through these fits, thermodynamic fits, what did we refer to this as? It was some certain sort of baseline. Do you remember? We always had a straight line and then we were fitting it. It was this is essentially your what? Unfolded baseline, isn't it? This is essentially unfolded baseline. So, what you do is unfolded baseline means what? Unfolded baseline means these are your points, and these are your points where it is essentially unfolded to the right of the curve. Now, you extend it, and if you have done it correctly, then every point on that curve would give you the signal for the corresponding unfolded state at that denaturing concentration. Okay, so, you can see here. So, this one would correspond to 2 molar and all this case, all these things. So, what do you mean by SU predicted? What do you mean by SU predicted is this: before you started mixing, that means even before the protein at 4.5 molar guanine hydrochloride was mixed, okay, what was the equilibrium prediction? What was the equilibrium value? The equilibrium value was here. So, it was 4.5 molar. So, this is 4.5 molar. So, this is 4.5 molar. This is before you started mixing. Okay? This is before you started mixing. Now, think about this. After you have mixed, coming along the same line, after you have mixed, what was your final concentration? 0.7. Okay? If the final concentration is 0.7, it should be somewhere here. This is your SU predicted 0.7, because it is along that unfolded line. But look at this. If you remember the curve, if you go back, right, here it is. What is the value here? It is about 0.5 something, right. Now, what is the value here? It is much more than 0.5, isn't it? It is what? It is kind of say 0.75 or so. So, whatever you are predicting based on your equilibrium value is 0.75. Whatever you are getting as the first time point from your stop flow is which one? It is not 0.75. What are you getting? You are getting this one from stop flow. So, what does it mean? It means this difference is essentially what? this difference essentially is your burst phase, because this you can never pick up. That is your predicted based on thermodynamic considerations, based on equilibrium, but what you get from kinetics, because if your instrument limitation is from S0, which is not from 0.75 but from 0.5. So, that portion you miss actually. Okay. So, this is what your burst phase refers to. So, if you would be doing this correctly, if you would be doing the kinetics correctly based on whatever limitations you have, you can always match these two things, it is not an issue, but you have to know what you are looking for or what you are going after. Okay. So, good. So, the drawback of this one, obviously you can realize the dead time is close to about 1 millisecond or so. What I said was you can go even down to 500 to 600 microseconds possibly if you are really good at the instrumentation, right. But the good thing is this, guys, the good thing is you can do it with a very small amount of sample, and I said it can be anywhere between 100 to 400 microliters of sample you can easily use for this one. Okay. So, now we need improvement. This is stop flow. What happens if we do not stop the flow? Okay. So, then the next one is referred to as a continuous flow technique. So, look how this is different, or look how this is similar actually. The stop flow had 2 syringes, right, syringe 1 and syringe 2. Now, this one also has 2 syringes, say syringe 1 and syringe 2, but anywhere in the rest of the apparatus do you see a third syringe? You do not see a third syringe, right, there is no other third syringe. You look at it, no matter how minutely look at it, there is no other third syringe. So, that means that syringe which had the function of stopping the flow is not stopping the flow anymore. Okay. So, essentially what is happening? What is happening is the same thing in syringe 1 you take protein and denaturant, in syringe 2 you take buffer, okay. Then you push them together with the syringe drive, this is your syringe drive, you push them together and then they will mix. So, this is your mixture. So, this is your mixture, okay. They will mix here. I will show you a blown up portion of the mixer later. Okay. Why is it called continuous flow? It is called continuous flow because once you mix these two systems, right, you are not stopping the mixing. That means you are not stopping the flow. You mix these and you allow them to flow. So, that means you allow them to flow along this line. You allow them to flow along this line, and this is your observation cell, right. That means this tubing you are looking at, this is where the solution is flowing and you are observing for detectable fluorescence changes. I repeat, you have mixed these two solutions, okay, in the mixture. I will show you that to you in the next slide or the next to next slide. After you have mixed them, you have let the protein or the mixed solution be as it is, you have not stopped the flow. So, what has happened? So, think about this. The difference is in stopped flow, the syringe stopped its flow, but the protein was not flowing anymore, right, because it has stopped its flow. Now, the protein was responding to whatever change it had to. In this case, what is happening is you have mixed it, and after mixing the solution is going on flowing, that is why it is called a continuous flow. Now, tell me, how is the protein responding? The protein is responding in the same way, but because this is the tube where it is flowing through, right, you have not stopped its flow. Now, think what will happen at the very initial portion of the tube. Suppose I have done the mixing, the protein would still be more or less in its unfolded state. As I move down, what is happening? The protein is slowly moving towards where? Its folded state. So, that means the distance it travels along that flow tube can be transferred to what? Its time, provided you know the flow rate and all these things. So, again you are not stopping the flow, you are allowing the solution to flow through, and the amount of and the amount or the distance it flows can easily be converted to time, and that time is actually the time which has elapsed since you have started mixing. And at these time points you take fluorescent intensity signals, you record those, and you get the kinetics. Is it clear or not? Is continuous flow clear? Is the difference between continuous flow and stopped flow clear? Right, that is why it is called continuous flow. You are not stopping the flow, okay, you are just letting it flow continuously. Okay. Sakshi, are you sleepy? No. Anyway, she is really looking at us like a face. I don't know what face is that, but okay, sorry for boring you. Now, because this is your observation cell, like the stop flow, you need something to observe. So, you can see here you have the lamp, here you have a monochromator, do not worry about the monochromator. So, the monochromator ensures this, it is a monochromator, right. Mono means single, chromator means color. So, it helps you figure out only one color out of a mixture of colors, right. And then you have a lens, then you have a cylindrical lens. You can see what happens is the lens kind of broadens your beam and then it focuses on the full cell, that is the continuous flow cell through which the protein is flowing. Okay. Now, how do you do the detector collection? If the detector is here, it is called a CCD. You know, I will not tell you what a CCD is, it is essentially a charged coupled device. If you guys have digital cameras, all these digital cameras are equipped with this. Okay. But anyway, then you collect the signal based on time points. I will show that to you. Let us go forward. So, the reaction in this case is still triggered by turbulent mixing, but in contrast to start flow technique, the progress of the reaction is observed under conditions of constant flow as a function of the distance from the mixing point. Okay. Now, try to realize the advantage of this. The advantage of this was, or this is, as compared to start flow, is even after the mix, even after in start flow, that observation cell had to be full, the syringe would come back and then it would get an upward thrust, that means stop, and it would stop it. But see, what it means is, from the moment that solution comes into the observation cell and the syringe gives a signal to stop it, that time you are still missing. In continuous flow, what you are doing? You are just mixing and letting it go. So, that is an advantage, you are gaining in terms of dead time, right, because you have stopping the flow, that means you can look at it from a faster time, that is one. But tell me, what is one major disadvantage? You require more amount, excellent, you require more amount, good. Second, the second is this, remember when we are talking about the flow, when we are talking about the flow being converted, flow rate, right, going to this distance and then distance being converted to time, what we are assuming is throughout the time we are monitoring it, its flow is still the same. But think about this, the moment you mix it, depending upon how you mix it, only over a certain distance would its flow be the same. After that, what would happen? The flow would not be the same. It is like rivers flowing through, right, at the source obviously it is coming down, at the source it would be pretty fast, but it is coming down a slope. But even then, if you are pumping some water, right, if you are pumping some water, what would happen is, very close to the pump, what would happen is, it would be very fast. You move far out, what would happen? The tide would slow down. The same thing happens here. That means, for the constancy of the flow to remain, you have to put in a turbulent mixing, and even if you do that, only over a certain time, that means only over a certain length of the cell would the flow remain constant, because after that the flow changes. So, the time interval now changes. Okay. So, the limitation is, in stop flow you do not have this, the limitation is in continuous flow you cannot monitor it for S infinity, because you are limited by that length of the flow cell over which it has a constant flow velocity. That is the limitation of continuous flow, it is a major limitation actually. Okay. So, thus continuous flow can achieve much shorter dead times than stop flow, right, just discussed. The disadvantages, as was pointed out, since it is continuous flow, huge amounts of sample are required. Now, again realize this, in stop flow you are stopping mixing, in continuous flow the syringe is always being pushed, pushed, because you have to maintain a continuous flow, right, because if there is no flow there is no signal, as simple as that. You push and you push on until what? Until you do not have any sample, you have run out of sample. Okay. So, that obviously is a huge disadvantage, especially for expensive proteins or expensive chemicals if you are using those. Okay. Now, this is, you are really looking at the instrument now, this is a zoomed in portion of the mixer. Now, see what they have done, you have to maintain turbulent mixing. Okay. You have to maintain turbulent mixing to maintain a decent enough flow rate over a certain length of the capillary or the flow tube. So, first of all, what is this 250 micron channel? This is your flow channel. Okay. So, this is, you can see this is your flow cell and this is your flow channel. So, what do you mean by the flow channel? Flow channel means after mixing the protein and buffer is flowing through this. Okay. So, this is where it is flowing through, good. Now, but before flowing it has to get mixed. So, the way it is done is, you see this is a platinum wire, you can see there is a platinum wire out here, right. So, this is the platinum wire, right. Now, at the end of the platinum wire you can see there is a small circle. So, the platinum wire has been drawn out into a circle. So, what they do is, you have two solutions, right, two syringes. So, one syringe solution comes like this and the other syringe comes like this. True. So, this is your inner capillary, you can see this is your inner capillary. So, whatever space you have, the solutions come through this, okay. You are pushing these two. Now, what people have found out is, if you push it with enough force and you make the solutions slide over a sphere, the mixing is very turbulent, okay. And because the mixing is very turbulent, then mixing is very fast. So, that is why they have it drawn out like this. Now, this is an experimental method, obviously people have spent time behind doing this, okay, but this was discovered some time ago, okay. So, once you do this, then the mixed protein starts flowing out, okay. Based on this instrument, or the instrument I just showed you, based on this instrument, okay, the dead time is 45 microseconds. This is your dead time. The dead time is 45 microseconds. Now, tell me, what was the dead time for your start flow? About 1 millisecond, right. Can you imagine the improvement you have done just by removing the stop method or just by removing the stop syringe? It is a huge improvement. Now, whether it is more than enough, that is a different issue, that will depend on the system, but definitely it is a huge, coming down from 1 millisecond to 45 microseconds, it is by no means small, okay. Now, what will happen is, because this is the flow cell, you will be getting data points throughout the flow cell, okay. So, these are your data points, you will be collecting. So, these are your data points, because along the flow, that means along the length of the flow tube is your time, that is what it means. Now, what do you mean by that? Okay. So, the flow cell in this case is 10 millimeter long and 250 microns wide, okay, 250 micrometer. So, here the first reliable data start from a point which is about 600 micron downstream from the bottom of the sphere. You remember the sphere over which the mixing occurred, right. So, from the bottom of the sphere, if you take a ruler, draw a distance of 600 micron, then the 600 micron is the first point where you start taking reliable measurement. Good. Now, what does this translate to in terms of time? Consider a linear flow velocity of 10 meters per second. If that is the case, then 600 micron travels or translates into travel time of what? 600 microseconds, right. So, at the first data point, that means the protein is already aged by what? 60 microseconds. So, this is how you do it. Now, do you understand the meaning of distance being converted to time? So, at whatever point you would take along the flow cell, whatever distance it is from the mixer, you know exactly, depending on the flow rate, what time it corresponds to, and that time you put on the x axis and you put your fluorescence intensity out there, and then you will get the curve again. Clear or not? Not many of you are nodding your heads. Is it from not understanding, or is it from because you are too tired? I have to know the difference now. Anyway, again, if you move along the flow cell, each point of the flow cell, that is the distance you have moved from the bottom of the sphere, can be converted to a time point. The same thing you did for the stop flow, but you did not have to do that, the machine itself did it for you, right, the software rather, okay. So, what is the main limitation? The difficulty in acquiring data beyond 3 milliseconds. Now, this is what I was referring to. Based on 3 milliseconds, you can calculate, right, how much distance I can go. Beyond that, I cannot go anymore, because my flow now becomes very erratic. I do not have a constant steady flow, and hence I cannot take data beyond that point of 3 millisecond, right. So, this is the disadvantage of, one of the disadvantages of a continuous flow technique, right. Okay. So, obviously a continuous flow does a good job in giving you a very faster, that means allowing you a very small dead time as compared to stop flow, but then it has to stop lot before your S infinity, because the S infinity is not necessarily reached at 3 milliseconds. That means your protein might not have stopped or your protein might not be done refolding at 3 milliseconds. It might take a longer time to refold. Then what would you do? What would you do then? You stop your experiment, go home, sleep. No? What would you do? Good. So, that means you combine the continuous flow with what? Stop flow. So, you can combine these two techniques. You can take the advantage of both these techniques, combine them and get a really decent time window. Okay. So, here, so this is what I was saying. So, this is your position which is getting converted to reaction time. This is your flow cell you are looking at. So, typical flow rates are 0.6 to 1 milliliter per second, which results in linear flow velocities of 10 to 16 meters per second, right. And this was 250 micron by 250 micron cross sectional area, right. So, it is 0.25. Now, this is the other part. See, suppose this is the time point. So, suppose this is your, what was the first time point for data collection in this case? Do you remember? 600 micron, right. So, let us say this is 600 micron. Okay. This is the first time point, right. Now, as you move, this is T1, this is T2, T3, T4, T5 and so on, right. Okay. Now, first look at the intensity of the color of the blue line, which is this is, so this is the blue is the flowing solution. Why do you think the intensity is changing from more intense to less intense? Why do you think so? Yeah, we are mixing, but then why is the intensity changing? Yes, but why is the intensity decreasing? Because you are talking about cytochrome C. Remember, the tryptophan intensity would be decreasing as you go to the folded state, right. So, here in the unfolded state you start with a very maximum intensity, that means very high intensity. As you go forward, the protein folds, tryptophan intensity decreases, and hence this color shading also goes in the lighter direction, right. Number 1. Number 2 is, here is a problem. Now, try to realize the problem. The problem is, if I have say one detector, and if I have to take fluorescence intensity points at T1, T2, T3, T4, T5 and so on, and say this is Tn, right. And if my detector is a point detector, that means it can only take one data point at one time. What will I have to do, or what will you have to do? What you will have to do is manually or by some other, by writing a program, you would have to take the detector and slide it, isn't it, along the flow cell. Do you realize what I said? So, suppose this is your detector, okay, and suppose this is a detector and the detector takes only one point. It is a point detector, it takes only one point, one fluorescence intensity at one time point, that means at one distance. Okay. So, suppose now this one takes at 600 micron, then for the next one you will have to move the detector along the flow cell. Okay. So, that is a bad way of doing it, right. Now, what would you do? Instead, what you do is, okay, why cannot I do this? Instead of having one detector, I can have what? A series of detectors at different time points. So, that means if I cover almost the whole flow cell, right, with different detectors, I will have enough information about my different time points. Okay. Now, being really ingenious, what you can think about is, why cannot I take one detector and use that one detector to get all the time points simultaneously? It is called an array detector. An array detector means it is like an array detector. That means if you are talking about one detector, which is a one point detector, it has one detection element. An array detector will be having what? A series of detection elements. It is called an array, right, a number array. So, it is a detection array, a series of detector elements, and hence if you put that here, each detector element would get the time point, would get a different time point along the flow cell, and hence you will get the kinetic trace. Okay. Now, that is the idea. This was the drawback initially, because you will have to move your detector along the flow cell or along the line. So, what people have come up with now, and this is a real good advancement, is something known as a CCD. A CCD is referred to as a charge coupled device. So, what it does is this. Okay. So, you have all these fluorescence intensities coming here. A CCD is broken into pixels. You do not have to know this, just listen to me. So, that means it has many pixels, say it has say 1000 by 1000, say 1000 by 1000, okay, just an example. So, that means an area has 1000 by 1000 pixels. So, what you can do is now you can take one, you can say one pixel corresponds to this, pixel is a small house, another pixel, a small square corresponds to this, another pixel corresponds to this, another pixel corresponds to this, and so on. Okay. So, the CCD can be programmed like that. So, instead, so essentially what you are doing is now if you go back to this slide, okay. Now, you can see the CCD detector. Can you see the small squares out here like a checkerboard, like a chessboard? So, these are your pixels. So, the pixels now try to realize this. You can see this beam of light coming out, right. This is one beam of light, this one, and this is another beam of light, right. So, that means you have the full fluorescence beam coming out. Now, understand the significance. This is your flow cell, isn't it? This is your flow cell through which it is flowing. You look at the beam, isn't the beam covering the whole flow cell through which the protein is flowing? What it means is, because you have covered the whole flow cell, that means no matter where you are at any given time, at just one shot, you are collecting all the respective intensities with the CC at the same time, because your instrument is designed in such a way with lenses and all these combinations that the whole cell is being focused at one point, and then the detection is also occurring from there, from the whole cell at one point. Clear or no? Okay. So, this is how the excitation is. You can look at the excitation. This is excitation, right. See, the excitation is not a small line, it is a band. What does that band cover? That band covers the whole length of the flow cell through which your protein is flowing. Okay. Now, once that is done, then because the protein is flowing, it is also emitting, that means fluorescing throughout the flow cell, and then you collect that with a combination of filters and lenses on your CCD, and then what you get is this. At each and every time point, you have a certain fluorescent trace. So, let us say this is T1, this is T2, this is T3, this is T4. Now, let me just do a qualitative plot. T1 would be high, the highest, T2 would be little low, T3 would be lower, T4 lower, and so on. And so, if you join this, what would you get? We are going to get another kinetic trace, right. So, this is how you get a kinetic trace from a continuous flow. Only in this case, you are stopping the flow, but you are taking time points along the flow cell to get the fluorescence intensity. Pin drop silence. कुछ अंदर गया कि नहीं? Full reflection या full reflection भी problem है, full transmission भी problem है. कुछ तो retention होना चाहिए. Now, did you understand the continuous flow technique, right? It is really important you understand it. Why? Because this is what is done presently, this is what quite a few groups have, and people are still working on it. And if you would be doing research, depending on which group you land into, you might have to work on a development of this technique. That means you make a faster dead time, that means you make a smaller dead time, that means you make a faster continuous flow, and people are still trying to bring about improvements on this technique. Okay. These are by no means old, these are very recent techniques, modifications are still being done, guys. Listen from me. Okay. Now, let us look at the kinetic trace under continuous flow conditions. So, this is under continuous flow, you can see this is the first point I started taking data, right, the small circles. But look at the problem. The problem is I start from here, but where do I end? I am not ending close to 0. Where am I ending? I am close somewhere at the top, right. Why is it that? It is because I have that limitation, right. I cannot go beyond 2 or 3 milliseconds. That means anything beyond that I cannot follow using continuous flow. So, I have to stop before. So, that means I start very early, but because I start early I also stop early. Essentially that is what continuous flow is doing for you, right. Now, So, this is a typical case where you are taking cytochrome C at pH is equal to 2, at pH is equal to 2 it is essentially unfolded, low pH, you know it is a pH denaturation. Then what you do is you mix it with a high pH buffer and bring it to a final pH of 4.5, and so it starts folding again at 4.5. And these are the two time constants, see these are the two time constants. So, you have fitted using that whatever equation I wrote, one is a 57 microsecond, right, and the other one is a 454 microsecond, right. Now, these are time constants, these are not your K's, these are taus with the corresponding amplitudes. See one has a amplitude of 60% and the other one has an amplitude of 29%. Now, you can realize why it does not add to 1. The reason is your decay is not complete, because you have to stop at about what 2 milliseconds or so, your decay is not complete. So, how would you know it? Because you have further components which you cannot see, right. It is a problem with the method. So, now as you guys suggested, what you do is you combine both of these. So, here from here to here is a continuous flow, you can see this is a continuous flow CF, I am writing it on the top again, and beyond that here is a stop flow technique. So, that means you take two, you combine these two to get the full trace, right. Now, look at the x axis, this is your log time. Tell me what does minus 4 to 1 mean to you in terms of a log time? What does minus 4 to 1 mean to you? Minus 4 is how many seconds? If log time is minus 4, it is how many seconds? 10 to the minus 4, which is 100 microseconds. What was the dead time of our continuous flow? 45 microseconds, right. Dead time was 45 microseconds. So, this 100 microsecond is coming from the continuous flow, right. Now, you move forward, the last one is what? 10, is not it? 1 is 10, right, 10 seconds. So, 10 seconds cannot come from continuous flow. Where is it coming from? Stop flow. So, now if you go from minus 4 to 1, how many decades of time have you crossed? Minus 4 to minus 3 is 1 decade, right, it is a 10, right. Minus 3 to minus 3 is another decade. How many decades of time have you crossed? So, minus 4 to 1 is 6 decades, right. Minus 4 to 0, 4, rather, well, how many? 1, 2, 3, 4, 5, 6, right, 6 decades in 1, including minus 4. That means, using this combination, you have been able to monitor a protein folding from or over 6 decades of time. Realize the importance of this. This time span is not easily achievable in any other technique. Okay. So, that means you are monitoring over 6 decades of time. Where do I write? Let me go forward first, then I will see. Okay. So, now, so this is 6 decades of time over which you monitor your protein folding. When you had only continuous flow, how many time constants did you have? 2. Look at the first two, 57 and 454. Now, when I have used the stop flow, how many more do you have? You have 3 more. So, these 3 you were missing when you were doing the continuous flow. However, when we are doing the stop flow, you are missing the first 2. Okay. So, then some points about the combined continuous flow, which is CF, and the stop flow, the SF techniques. The stop flow has a dead time of about 2 milliseconds in this case, while the continuous flow has a dead time of 45 microseconds. Good. The combined technique or data have been plotted over 6 decades of time, right, and have been fitted to 5 exponentials. Now, this is important, right. It is not going to have for every protein. This is cytochrome C we are talking about. Under the folding condition chosen, only 15% of the total fluorescence change is observed with stop flow experiments, whereas the CF data, which is the continuous flow data, resolve an additional 50% of the total signal, right. So, do you realize the importance of this? So, go back and see, from here to here is almost 50% of the total signal, from here to here is just about 15 to 20%. So, if you were taking stop flow, you would be missing out on what? 50% of the total signal, the initial part. when you are using continuous flow, you are getting that 50%, then but then you are missing the rest which you are getting from stop flow. Okay. Right. So, the result in additional 50% of the total signal associated with the refolding between 45 milliseconds and 1, sorry, this should be microsecond, 45 microsecond and 1 millisecond. And this is the last point I will quickly introduce before I end the class. You know, people are smart, the people just do not sit, they try on improving these things. So, what they have done is now they have given rise, or they have come up with a technique known as continuous flow technique, the same continuous flow technique, but it is based on microfluidics. Have you heard of the word microfluidics? Okay, this concept is very simple. Micro means obviously small, fluidic means you are talking about flow of fluids. That means, if you are talking about microfluidics, you will be talking about flow through micron size channels, that means channels which are very small. See? So, if I show you what it is based on a technique called hydrodynamic focusing. As it says, hydrodynamic focusing is a technique relying on squeezing one of the streams in a 4 microchannel intersection by 2 side streams and reshaping it downstream into a thin sheathed film. Okay. Lot of words, but the take home point is very simple. This is what it is. This is a protein plus denaturant. Okay. Now, here there are no syringes right now. Here you can have syringes attached to these channels. We are talking about a channel. This is a micron size channel. The width of this width you are talking about, this width is typically 10 micron. What was the width for your continuous flow technique? Do you remember? 250 micron. Someone was awake. 250 micron. Okay. So, you can see how small it is, right. Now, because it is still a continuous flow technique, but your flow cell is small in size, that means the amount of sample you will be using is also small, because if volume is small, right. Now, what you do is, because this is the protein plus denaturant, you have to look at refolding. What you do is, from these 2 sides you flow in what? Buffer. So, see what happens. Okay. It is like if you are traveling in a crowded train or a bus, you are standing here, initially the bus was pretty empty, now it is very crowded, initially you are spreading your legs like this, now people come from all sides, say 2 sides, and then you are squished like this, right. So, the space you occupy is small, right. Now, the same thing is happening here. Initially, if these 2 side channels were not there, the flow would be like this. Okay. Now, what you are doing is, this is the protein and denaturant. Now, what you are doing is, you have 2 channels on these 2 sides, you are also flowing buffer from these 2 channels. So, what will happen? It will squeeze this small. Okay. Now, remember, these are flow techniques, this is a rapid mixing technique, right. So, mixing depends upon the distance over which you mix. So, the smaller the distance over which you will mix, the better it is for you, the faster you will mix it. Now, see what happens. Initially the flow was like this, right. This was your flow, this was the breadth of the protein flow. Now, what happens? You see the mixing flow, it mixes. If this is whole of 10 micron, over what dimension does it mix? It mixes, say, over 2 or 3 microns. Is it not really small? So, the actual mixing is occurring over what? Just a very small area, and after that the solution flows like this. So, this is referred to as hydrodynamic focusing. That means, you are focusing it pretty hard from the sides on a channel which is going like this, and you are squeezing it into a thin stream. I will tell you in the class tomorrow. Can you imagine what the dead time is achieved in this case? Guess. What is the dead time? Any guesses? If you come very close, a coffee. You give me a coffee now. Okay? Now, you treat me with a coffee. That was a bad guess. Everyone was less than 45 microseconds. Okay, so all of you, take note of this point. Yeah. Any ideas? Come on, come on. The faster you tell, the faster you go. Come on. Huh? 1. Pobre. So you get a coffee and a sandwich. It is 5 microseconds. So it is 5 microseconds. So that is the fastest you can mix it. The mixing dead time is 5 microseconds, and after that you can look at it. Okay, so this is called microfluidic mixing. People are really doing it nowadays. Okay.